Good morning. Today we're going to start talking about Chapter 18, Aldehydes and Ketones. We're first going to start with the introduction, which just reviews some of the main aspects of aldehydes and ketones that we need to understand. So, aldehydes and ketones are compounds that contain a C double bond O, which is called a carbonyl group, and that C double bond O has no other heteroatoms attached. In other words, it has only hydrogens or carbon groups attached. Now, an aldehyde is defined as having at least one hydrogen group attached to the C double bond O carbon, whereas a ketone has no hydrogens attached directly to the C double bond O carbonyl carbon. The abbreviation for an aldehyde, which is widely used in partially condensed structures, is CHO. There is also an abbreviation for ketones, which is less widely used, which is to write the carbon group, then a carbon and an oxygen, and then directly another carbon group. It's often preferred to put parentheses around the oxygen to indicate that the oxygen is actually, if we look up at the expanded structure, branching out from the direct line of the carbons. The three-dimensional structure of aldehydes and ketones is shown here. We can see that the central carbon has a steric number of 3, which means it will be trigonal planar. And in order to be trigonal planar, then, it's going to require sp2 hybridization. If we look at the orbital picture, we would have sigma bonds from this carbonyl carbon to the carbon groups, and also one sigma bond to the oxygen. And then out of the plane, there would be a pi bond. And finally, the lone pairs would lie in the plane with the rest of the atoms, and they would be in sp2 hybridized orbitals. All carbonyl compounds have a minor contributing resonance structure, and this has a fairly large impact on their chemistry. So what we can see is that because the oxygen is very electronegative, we can sort of imagine that there would be an additional structure where the oxygen pulls one of the lone pairs from the pi bond out onto itself. This creates 3 lone pairs on the oxygen and 1 bond, which would give it a negative formal charge. And if we look at the carbon, we can see that it would now have an incomplete octet, which would give it a positive formal charge. The importance of this is that when we look at how carbonyl compounds react, we generally find that electrophiles will react with the oxygen because of the partial negative charge that will form on. Whereas, in contrast, nucleophiles will prefer to react at the carbon because they will be attracted to the positive charge that's formed up on the carbon. We're now going to quickly review the oxidation states of carbon because the oxidation states provide sort of a roadmap for many of the reactions that we're going to look at going forward. We are not actually going to calculate oxidation numbers for the central carbons, although this can be done. Instead, what we're going to do is the organic chemistry shortcut, where we look at the central carbon, for example, this one, and we look at how many heteroatoms, how many bonds to heteroatoms are there from that central carbon to the attached groups. If we look at, for example, an alkane, which is only going to have carbons and hydrogens, that alkane carbon would have 0 bonds to heteroatoms. And therefore, that would be the most reduced form of the carbon. As we increase the number of bonds to heteroatoms, so for example, moving to an alcohol, where we have the central carbon with 3 bonds to carbon or hydrogen, and then 1 bond to an oxygen, we can see that that would be one step more oxidized. Note that because we're looking at bonds to heteroatoms, oxygen is a typical heteroatom, but there are other heteroatoms, for example, nitrogen, the halogens like fluorine, chlorine, bromine, and iodine, and then even electronegative atoms like phosphorus, sulfur, and selenium. As we move across then, we can have two bonds to heteroatoms. In our typical example, we would see that this would be an aldehyde or ketone with two bonds to an oxygen and then one bond to either a carbon or a hydrogen on each side. So this is the oxidation state that we're going to be working with most in this chapter. The other oxidation states increase the number of bonds of heteroatoms. So for example, a typical one with just oxygens would be this, where there's three bonds to heteroatoms, carboxylic acid, and then finally four bond to heteroatoms like carbon dioxide. If we look then, what we can do with our reactions is we can change the number of bonds to heteroatoms or change the number of bonds to hydrogens and carbons from this central atom. If we decrease the number of bonds to heteroatoms, so for example, going from 2 in an aldehyde or ketone down to 1 in an alcohol, we would be doing a reduction. So moving to the left on this chart would be reduction. In contrast, if we were to increase the number of bonds to heteroatoms, for moving to the right, that would be an oxidation. Finally, then, there is one more class of reaction which turns out to be very important in this chapter. It has no official name, interestingly enough, so I've given it the name heteroatom exchange. Because what we're going to be doing in this reaction is changing a bond from a heteroatom to a bond to a different heteroatom. So we're just exchanging the heteroatom at the end of the bond. Finally, then, while we can use oxidation numbers to define the number, the oxidation state of the carbon, generally what we do is we use the name of the corresponding example that uses only oxygens. So for example, the 2 bond to heteroatom 1 oxidation state would be the aldehyde or ketone oxidation state. The 3 bond to heteroatom would be the carboxylic acid oxidation state. We're going to quickly review the nomenclature of aldehydes and ketones. In reality, we covered this nomenclature in first semester when we covered really the basic nomenclature of all the important functional groups. But to review, we had a procedure for doing IUPAC naming for different molecules. What we would do is we would first identify what we called the highest priority functional group. There's a table further in these notes that will rank the priority, the functional groups in order of priority so that we can determine which would be the highest priority. We would also want to identify any unsaturations, which would be double or triple bonds. We would then use the identity of these functional groups and unsaturations to locate the parent chain, which would be the longest continuous chain of carbons that contains both the highest priority functional group and any unsaturations. We would then count up the number of carbons in that and get the parent chain name. We would then number the parent chain using the numbering rules, which basically more or less boil down to having the highest priority functional group at the lowest number possible, and then also numbering the unsaturations. Number the unsaturations and add their name after the parent chain name. We would number the highest priority functional group and add that name to the end of the name after the unsaturations. We would then number and name the substituents and list those in front of the parent name, and finally determine any stereochemistry. This table shows the order of priority of the functional groups and unsaturations, as well as how those functional groups are named, and in the case of a few functional groups, how they would be named if they were substituents. So we can see that really the order of priority is arranged around the oxidation state, with the high oxidation state functional groups being the highest priority, And then as we move down, so carboxylic acid, ester, amide, and nitrile are all carboxylic acid oxidation state. They have 3 bonds to heteroatoms. Then we have aldehyde and ketone, which are aldehyde and ketone oxidation state. They have 2 bonds to heteroatoms. We have alcohol and amine, which have 1 bond to heteroatom. And then we have alkene and alkyne. Here are the names that we would put into the compound name. So for example, carboxylic acid is named as an oic acid. Esters are O8 with an alkyl group in front, and so forth. We're mostly interested in this chapter in aldehydes and ketones. We can see that to name an aldehyde, we append the suffix al on the end of the parent and unsaturation names. We don't have to put a number in front of the al because aldehyde carbons will always be at end of a chain, and since they would presumably be the highest priority, they would be at number 1. In contrast, if we look at ketone, we append the suffix one to the end of the name, but ketones, being in the middle of a chain, could be at one of several carbons for very long carbon chains. So we would have to add the number where the actual carbonyl carbon was located in the chain. Finally then, I want to introduce you to some substituent names. It is possible to have ketones in a molecule, but then also a higher priority functional group. So for example, maybe an aldehyde and then also a ketone in the same molecule. In that case, the higher priority functional group would get the suffix, the ending. So we would have to name the ketone as a substituent. In that case, we use oxo. And it's very important to distinguish that it is OXO. There is a very similar substituent name for when we have an oxygen substituted in the chain. That name is OXA ending in A. So we have to make sure that we put OXO to make sure that we're indicating a ketone. We've already seen hydroxy for alcohols in a chain, and you may or may not have seen, but when there's an amino group, we use the name amino. Finally, then, if we look at our thing, alkanes, ethers, and halides are always substituents. They don't have a special priority, and they are always named as substituents, either alkyl, alkoxy, or halo. Looking at a few examples then really quickly. If we look at this molecule has an aldehyde, C double bond O, with a hydrogen directly attached. And it also has an alkene. So it has both a main functional group, which I've circled here, the aldehyde, and it has an unsaturation. So what we would do is we would determine that this chain of carbons here would be the longest carbon chain, and it has 4 groups, so that would get the prefix bute. We would then identify that the unsaturation starts on carbon 2 and goes to carbon 3. So we use the lowest number of the unsaturation, and then we append the suffix -ene. And then finally, because we have an aldehyde at carbon 1, we will put the ending Al. Now, because Al starts with a vowel, we will drop the E from our alkene name so that we get bute 2-ene-al. If we look at the next example, we have a ketone and we have an alkyne. So again, the ketone will be higher priority. If we look at the carbon chain, we have a total of 6 carbons, so that's a hex. The alkyne, which is the unsaturation, starts on carbon 5. That's the lowest numbered carbon of that unsaturation. So therefore, we put 5 and we use the suffix -ine. And again, we then add the ending ONE, which starts with a vowel, so we drop the E. Finally, we look and see that the ketone is on carbon 2, so we put the number 2 and then the ending -one. Hex 5-ine 2-one. Finally then, this is an example where the ketone is a substituent because we have two functional groups and it is the lower priority. So in this case, again, we have an aldehyde and we have a ketone. The carbon chain has 5 carbons, so it's a pent. There are no unsaturations, so we use ane, like in alkane, and then we add the ending for the aldehyde because that's higher priority, Al. The ketone then is on carbon number 4, and so we put the number 4, and then we use oxo to indicate that it is a substituent ketone. There are some special common names of aldehydes that you should have memorized. These are widely used, and it's very likely that you would encounter these in an experiment or in a standardized exam. The first one is this. This is the smallest, simplest aldehyde you could have. It has one carbon, carbonyl, and then it has two hydrogens attached. This is called formaldehyde. That's the common name. The second common name that we're going to look at is the aldehyde equivalent of acetic acid. It's two carbons. Carbonyl carbon would be number 1, and here's the hydrogen. This is called acetaldehyde. If you look at acet, you can see that that is probably derived from acetic acid, acetic acid, so acetaldehyde. Finally then, a benzene ring with just one aldehyde attached is called benzaldehyde. Ketones are interesting because they have also a systematic common nomenclature, which is very old-fashioned but is still widely used. In this systematic common nomenclature, what we do is we identify the carbonyl carbon, and then we look at the two carbon groups that would be attached to that. We name those as alkyl groups, as carbon groups, and we list them in front alphabetically. So for example, if we look here, we have a methyl group on this side, we have an ethyl group on this side, so we would call this ethyl space methyl space ketone. Just to remind you of a couple of these special group names, here's another example. We have a methyl on this side. This unsaturation containing group, the common name of that is vinyl. So this would be methyl vinyl ketone. There are also common names of ketones that you should memorize. This ketone here, if you look, it's like an acetic acid with a methyl attached on the other side. So again, we have that acet, and then we put the ending for ketone, acetone. This has an acet group, acete, right here, and then it has a phenyl group. So it is acetophenone, ketone, acetophenone. And then similarly, this is like a benzaldehyde with a phenyl on the other side, so benzophenone.